Thank you all for staying till the end of the day and gritting your teeth and sitting through the last talk. So I really appreciate that. So, as you might have guessed from the title, we are still going to be interested in combining the best from multiple worlds. And in this case, the worlds we are talking about are approximation algorithms and kernelization. I'm just changing the terminology for now because by now, as you all know, kernelization and FPT are pretty much the same thing. So, what are lossy kernels? Lossy kernels are, of course, what you get if approximation algorithms and kernelization algorithms got together and had a baby. Now, let me begin by reminding you the notion of kernelization as you've seen over the last 2 days. So if you remember, in kernelization, what we are trying to do is we are trying to come up with efficient pre-processing algorithms where the input is an instance of a parameterized problem, which is usually a pair I, k. And the objective is to, in polynomial time, come up with a reduced instance I prime, k prime, such that, of course, you don't want to flip the answer. Yes instances remain yes instances, and no instances remain no instances. And furthermore, the output is bounded polynomially in the parameter. Well, it is bounded by a function of the parameter if you just talk about kernels, polynomially in the parameter if you want to talk about polynomial kernels. So by now, you've already seen a few examples of kernels, exponential size kernels, polynomial size kernels, so I hope you know what these terms mean. Now, let's say you are designing a kernelization algorithm, and once you finish the design, you're going to hand it off to a colleague who intends to use it. So now your colleague runs this algorithm and says, look, this was very useful. I was able to significantly reduce the size of my problems. However, it is still too large for me to be able to solve it optimally. So I'm going to use a very nice 1.001 approximation algorithm that I have. Okay. So now the colleague comes and asks you, okay, can I pipeline this very nice approximation algorithm with your kernelization algorithm? So what do you say? You say, oops, sorry, because the model of kernelization we have talked about only promises that yes instances go to yes instances, no instances go to no instances, and it says absolutely nothing about how the quality of these solutions change when you do your reductions. So you do see that if I give you a 1.001 approximate solution for the reduced instance, whatever that means, you really don't know what to do with respect to the original instance. So this is one obvious issue with the definition of kernels as you've seen. And what you've seen so far essentially translates to the following. What you can guarantee is that an optimal solution here can be transformed into an optimal solution here in polynomial time. Because this is how you were proving the correctness of these reduction rules. You were always proving that if g, k or I, k is a yes instance, then here's a solution for I prime, k prime. And if I prime, k prime has a solution of size at most k, for instance, then you can pull it back to a solution of size at most k for I, k. So this is basically how you were arguing the correctness of your reduction rules. And in the process, what you were proving is essentially this, that an optimal solution here can be pulled back to an optimal solution back here. But as I pointed out, ideally, we would also want to pull back a 1.001 approximate solution back to a 1.001 approximate solution for the original instance. At least we would want to say something meaningful about the solutions for the original instance if someone gives me a good approximation for the reduced instance. I should be able to say at least something interesting. And this would be really ideal. But for technical reasons, if you are allowing this sort of a loss in the solution quality over here by your colleague, now you can tell your colleague, okay, fine, since you are incurring a loss of quality, I'm also going to incur a slight loss of quality when I pull this back. So formally speaking, this is what alpha approximate kernelization is. So alpha is just a fixed constant for now. And an alpha approximate kernelization algorithm is nothing but a polynomial time algorithm that takes as input I comma k as before. The output is I prime comma k prime as before. The size of I prime comma k prime should be bounded by a function of k as before. But the new thing is that if someone gives you a C approximate solution for the reduced instance, you should be able to efficiently, and by efficiently I mean in polynomial time, pull it back into an alpha C approximate solution for the original instance. So now, if you had a really good approximate kernelization algorithm, then you can tell your colleague, hey, look, here is this black box. Use it as you like. Pipeline it with whatever algorithms you like. I promise you that you will be able to obtain some meaningful information about the original instance. And of course, we call this a polynomial size alpha approximate kernel if the size of I prime is bounded polynomially in K. So I hope I have explained to you the issue with the standard definition of kernelization. And here is just a definition that appears to circumvent the issues, at least on the surface. What I'm going to try to do in the next 40 minutes or so is try and show to you that this definition actually leads to some interesting results, because without it, this is just a new model that we are proposing. So now let me try and tell you a few very quick, interesting results, which I hope will solidify your interest in this concept. So earlier you've seen that a problem is fixed parameter tractable if and only if it has a kernel. Okay? So what would the natural analog be here? So here, and this holds, a problem has an FPT time alpha approximation if and only if it has an alpha approximate kernel of some size. So this sort of an analogy is something what you desire, is also something that you get building on this model. Okay. I will not prove this to you, but I'll prove something similar based on which you will be able to see this proof also. Now the second thing, if you spend time thinking about the notion of kernels, you will have noticed that a problem is in P if and only if it has a constant size kernel. Because if it has a constant size kernel, clearly it is in P. You just do this pre-processing in polynomial time, solve it in constant time. And the converse is equally easy. What is the analogy that you would like? A problem has a polynomial time alpha approximation if and only if it has a constant size alpha approximate kernel. And again, such an analogous statement that you would like also holds with this definition. So if the statement is clear, I'll go ahead and give you a quick sketch of the proof. It's not very hard. So let's look at one direction, and it is the following. So suppose that we are given a polynomial time alpha approximation algorithm for a problem. Now I have to define to you this object, which is an alpha approximate kernel of constant size, which means that the output here should have constant size. So how do I come up with this object, assuming this object? So given I comma k, I'm just going to construct an arbitrary instance of constant size and reduce it. This is it. But now to prove that this is actually something that I promised you, I need to prove to you that if someone gives me a C approximate solution for this whatever that I outputted, I should be able to come up with a meaningful alpha C approximate solution for the original instance. So this is what the model requires me to do. And how do I do this? It's very simple. If you give me a C approximate solution for this, whatever this is, I'm just going to throw it away because this was meaningless, so your C approximate solution was also meaningless. So I'm just going to forget this, but I'm just going to take this instance I, and I'm going to run this assumed polynomial time alpha approximation algorithm to actually compute an alpha approximate solution and just return it. And since C is at least 1, whatever you return is definitely an alpha C approximate solution, whatever the C was. Right? So this is very straightforward. And now in the converse direction, suppose we are given this alpha approximate kernel of constant size. How do I come up with an alpha approximation algorithm? It's very simple. Given I and k, I'm just going to plug it in to this assumed object, which I am promised will output a solution, output an instance of constant size. Now I'm going to take this constant size instance, and in constant time, I'm going to find an optimal solution, which is nothing but a 1 approximate solution. So C here is 1. So once I plug it back here, the promised object guarantees that in polynomial time, we can compute an alpha C approximate solution. Since C is 1, this is an alpha approximate solution for I, which can be returned. So this is a very simple proof that a problem has a polynomial time alpha approximation if and only if it has an alpha approximate kernel of constant size. And the proof that a problem has an FPD time alpha approximation if and only if it has some alpha approximate kernel is very similar to the proof that FPT if and only if kernel. So I'll leave this as an exercise. So any questions so far? Great. So given this particular statement, when we try to design alpha approximate kernels, what are the things that we want to optimize? What are the parameters here that we want to optimize? So ideally, we want this alpha to be as small as possible. Ideally, we want the size of the output to be as small as possible. And ideally, we want all the computation to be as quick as possible. OK, but do we have some sort of baselines about the kind of alpha we should aim for, the size of the kernel we should aim for, and so on? So because of this statement, what we infer is that whenever you try to design an alpha approximate kernel, the alpha that you should be interested in should always be better than the best polynomial time alpha approximation that you're given. Because if you have, let's say, a 2 approximation for a problem, and then you're trying to get a 3 approximate kernel, there's no point, because we just saw that there is an easy 2 approximate kernel of constant size. So the alpha that you always think about aiming for should always be better than the best known approximation factor. And in the other world, similarly, the size of the kernel that you're aiming for should, for pretty much the same reason, always be better than the best known polynomial kernel. So for instance, you've seen a k-square kernel for vertex cover. And if you stare at it carefully, you can see that it is actually a 1 approximate kernel of size k square. And now if you want, let's say, a 2 approximate kernel or a 1.5 approximate kernel, what is the size you should aim for? Is there any point aiming for a size of k square, k cube? No, it doesn't make any sense. Because now you are allowing more inaccuracy in your kernelization. So the size that you aim for should always be better than k square. So this statement gives you a very interesting baseline to target when you start working on these problems. So what I would like you to take away from this segment is, whenever you start trying to design alpha approximate kernels or even ask the question, is there an alpha approximate kernel of some size? Immediately ask yourself, what is the best known approximation algorithm for this? What is the best known kernelization algorithm for this? So these are 2 questions that should immediately occur to you. And once you have the answers to these questions, then you have a good baseline to aim for. And if even these are already unknown, you have found yet another interesting question to work on. So win-win. All right, so let me give you a quick example of an alpha approximate kernel. Let's look at the very classic maxsat problem. So in this problem, you're given a CNF formula, and the question is, what is the maximum number of clauses that can be satisfied? So this is an optimization problem. And this problem is APX hard, which means it does not have a polynomial time approximation scheme or a PTAS, which means that you cannot approximate it arbitrarily close to 1. On the other hand, we do not have any kernel of polynomial size, as you might have heard, assuming some complexity theoretic hypothesis. So now, given this, it still makes perfect sense to ask for a 1 minus epsilon approximate kernel of polynomial size, because what you're trying to do is try to get the best of both worlds. Just like in Mehrab's slide, we had 2 stops, and she cleverly chose a plane. What we are doing here is we have 2 stops. That doesn't stop us from taking a plane, and the plane in this context is a 1 minus epsilon approximate polynomial kernel. So let me give you a very quick kernel. It's based on the following observation. So set d equals log 2 over epsilon, where epsilon is any fixed constant that you gave to me. Okay, it's a fixed constant between 0 and 1 for now. And based on that, I set d. And now I check. Are there at most epsilon m over 2 clauses that have size at most d, where m is the total number of clauses? If this happened, the observation is that any random assignment is going to satisfy all but epsilon m clauses anyway. Which means your job is pretty much done. You don't have to do anything. If this is the case, then a random assignment is going to satisfy this with good probability. Okay? Otherwise, what happens? Otherwise, what you're saying here is most clauses are actually small. And if there are no duplicates, what this means is that the number of clauses is bounded by n to the d roughly, and d in this case depends only on epsilon, which is a constant. So the number of clauses you're left with in this case is just a polynomial in n. So based on this observation, you have a very simple, for now randomized, 1 minus epsilon approximate kernel. What does the kernel do? It stares at the instance and it just outputs the same instance. It does nothing. So now if someone gives me a C approximation for this reduced instance, what do? So if someone gives me a C approximation for the reduced instance, it is either a C approximation for the original instance because they are the same thing, or I can actually throw that away and find a better 1 minus epsilon approximation because we are in this case. Okay, so what you end up with is sort of a cheating kernel. I actually did nothing. I just took the instance, did some case analysis, and just output either the same instance or some garbage. This is all that I did. And at this point, you might be wondering, okay, is this all there is? So there were some interesting theorems, but now when it comes to real examples of approximate kernels, are they all like this? Do you have some sort of a win-win situation in every instance, which means that you don't have to do any work, which means, unfortunately, no papers? Actually, it turns out this is not the case. And in fact, approximate kernels have been around in the wild for many, many years. So here is a quick example. So do you know the Steiner tree problem? If you don't, let me tell you. If you do, let me remind you. So in the Steiner tree problem, you're given a graph G and a vertex subset R, and the objective is to find a smallest connected subgraph containing R. This is what is called a Steiner tree. Now, this problem has a constant factor approximation, but you know that you cannot have a p-task. And if you parameterize it by the size of R, which is the size of the terminal set, then there is a 2 to the R size kernel. And unless some bad things happen, there is no polynomial kernel. But does this stop us from asking the question whether there is a 1 plus epsilon approximate polynomial kernel for every epsilon? Nope. This is a very valid question. And turns out the answer is yes. And if you notice the year over here, it's not 2017, it's not 2007, it's actually 1995. So it turns out that all of the current Steiner tree approximation algorithms actually start by computing a 1 plus epsilon approximate kernel of polynomial size. This is what they do. They start by doing this, and then people have added on more and more cleverer heuristics and clever branching steps. But the first step is just compute a 1 plus epsilon approximate kernel of polynomial size. So what I wanted to convey here is that this object has been around in the wild, and this is actually non-trivial. It's actually non-trivial enough for me to not be able to present the proof here. Okay. So another example is something that you might be a bit more familiar with. I really hope you remember the name, at least. Partial vertex cover. And the FPT approximation that Meirav just presented is actually nothing but the following. Step 1, compute a 1 plus epsilon approximate kernel. Step 2, brute force on it. This is actually what she told you. And again, here this was done in 2008, where Daniel Marks phrase this without using the language of approximate kernels, because all he was looking for was NFPT approximation algorithms. So, to sum up this slide, what you've already seen, if you're not convinced already, it's a very good exercise and you'll end up actually learning the partial vertex cover algorithm really well. Try and prove for yourself how you can get a 1 plus epsilon approximate kernel of polynomial size for partial vertex cover. And now I'm trying really hard to convince you that the maxat example wasn't what most examples look like. So here are many problems, most of which have been instrumental in the theory of kernel lower bounds. So there are a lot of kernel lower bound results starting, which are based on reduction starting from these problems. But it turns out that for a lot of them, you actually have interesting, highly non-trivial, approximate polynomial kernelizations. Okay. So just a quick reminder of problems parameterized by solution value before we actually get to some concrete problems, which I hope will illustrate the points that I'm trying to make even better. So if you remember, K in the context of parameterized approximation was sort of a threshold. If you remember, Meira was doing some cutting beyond K. So if you're looking at minimization problems, the intuition is that all solutions beyond K are just equally bad for us, so we don't care. So this is just something that you need to keep in mind, but it's not critical for this particular talk. So if you feel like this confuses you, feel absolutely free to forget it. Okay, so let me give you one concrete example to sort of give you an idea of the type of arguments that one uses in designing these approximate kernelization algorithms. So by now, I'm pretty sure you're all familiar with the vertex cover problem. The connected vertex cover problem, the only additional constraint is that you want the vertices of your solution to also induce a connected subgraph of your original graph. Simple enough constraint. Unfortunately, it changes everything. So a quick survey on this problem. So this is known to have a 2 approximation, and it is known that under the unique games conjecture, this is pretty much the best you can hope for. It has a 2 to the k kernel. If you don't see this immediately and you want to zone out for the rest of the talk, here's an exercise, try to prove it. And it is known that unless some complexity theoretic collapse happens, there is no polynomial kernel for this problem. So this problem falls right in our wheelhouse. We have stop, 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 stop everywhere. So now this means we can ask the question, is there a 1 plus epsilon approximate polynomial kernel for this problem for every fixed epsilon? So at least the question makes perfect sense. There is nothing on this slide that precludes you from asking this question. Okay. So before I explain this approximate kernel, let me remind you of the normal kernel for vertex cover. So in the normal kernel for vertex cover, what we did was we essentially partitioned the vertex set into 3. We had the set H of high degree vertices. These are vertices of degree greater than k. The reason why this set is interesting is because we know that any vertex cover of size at most k contains every vertex in H. Right? This is what was called the bus rule. And I is just the set of vertices whose neighborhoods are contained in H, which means this is an independent set, and R is the rest. And you already saw that the size of H better be at most k, otherwise you cannot have a vertex cover of size at most k. The size of R better be order k squared, because otherwise you cannot have a vertex cover of size at most k. And finally, what you did was you just threw out I, because what role were these vertices playing in your instance? If I tell you that H is going to be part of every vertex cover that I'm interested in, you could just throw out I. Right? Modulo one small detail. When we throw out the vertices of I, we forget that some vertices here might be high degree vertices, because these guys could be high degree vertices because of neighborhoods in I. So there is one subtle point here in my description, which is that before you throw away I, you need to mark at most k plus 1 neighbors of each vertex in H here and throw away the rest. This is just a small subtle point that it'll be helpful to remember. And so this was the bus k-square kernel for vertex cover. I hope you remember this. Now, why doesn't this work for connected vertex cover? Well, obviously, this one step where I threw away vertices is not really a smart thing to do when it comes to connected vertex cover. Why? Because even though these vertices here may not be required to cover edges, which is true because the vertices here are doing all the covering, these vertices do have some role to play in the problem. And that role being providing connectivity between other vertices. So you cannot just greedily throw away vertices of I. So in order to get a 1 plus epsilon approximate polynomial kernel, what we are going to do is show to you that even though you cannot throw away everything in I, if you relax your target to only preserving approximate solutions, then there is a small subset of I which you can keep and you're happy. This is it. So what we are using here is the fact that we are only interested in approximate solutions and not optimal solutions, and we are using this to win by showing that there is a small number of vertices in I which we keep and we are fine. So formally speaking, this is what our approximate kernel actually does. What we are going to prove is given G and K, there is a polynomial time algorithm that immediately concludes that there cannot be a vertex cover of size at most K, or it outputs an instance G prime comma K, which is reduced, that is point C, and by reduced now we allow the exponent of k to depend on epsilon, because epsilon now is a fixed constant. So k to the some function of epsilon is still k to the big O of 1 for us. So that is the first thing, that we want a reduced instance. The second property is that if your colleague now comes and finds a connected vertex cover of G prime, you can actually conclude that this is also a connected vertex cover of G. So I will give you this property. And finally, I tell you that if your colleague has a really good approximation, then in fact, because of property 2, that is also a really good approximation from my original instance. That is because of property B, which says that the best connected vertex cover of G prime is not much larger than the best connected vertex cover of G. So when you reduce this instance, you're throwing out some vertices of I. But in this process, although hypothetically you could have blown up the size of your best connected vertex cover by an arbitrary amount, I promise you that if you do it carefully, you will not be doing that. So let me describe this polynomial time algorithm to you. It's very simple and it follows along the same lines as the bus kernelization. And there'll be one point where we observe that the bus kernelization failed, where we will do one non-trivial step. Okay, so what are we going to begin with? We are going to begin by running the known 2 approximation algorithm. This is a polynomial time algorithm. And if the output is greater than 2k, then you know that the best connected vertex cover is already greater than k, and you're done. Otherwise, you know that the best vertex cover has size at most 2k. So now you go to this previous picture as before, except that now H is just vertices of degree greater than 2k. And now what you are going to do is look at the vertices in I. These are the vertices which, if you remember, I pointed out play an important role with respect to connectivity. Now, if I ask you to quickly give me some vertices in I which do the best job of making this of inducing connectivity, what you would most likely do is go start picking up vertices based on their degree. Just pick up vertices of high degree as long as possible. Intuitively, this is what you would do. And it turns out that this is sufficient if you set all the numbers correctly. So formally, what you would do is, so you pick a D as before in the maxstat example, which is inversely dependent on epsilon. And as long as you have a vertex V which sees many connected components of H, you just force this into your approximate solution. And one easy way of forcing it is just add a pendant vertex on it. That is a vertex of degree 1 with this guy as the only neighbor. So this is an easy way of forcing a vertex to be picked. And we do this as long as you have a vertex here that sees at least D connected components in S. Which means that you stop when every vertex in I sees at most D connected components. So this is your stopping condition. And how many vertices do you add when you do this iteration? Each time you add a vertex, you're reducing the number of components by at least 1. And initially, you have at most 2k vertices. And if you're reducing the number of components by 1, it means that the number of iterations here is at most 2k. OK. And this, based on D, is only an epsilon fraction of your opt. So what have you done here? What you have done here is you've picked up epsilon opt vertices, and you've greedily forced them into your solution. This is all that you've done. OK? And what this allows you to prove is that henceforth, if you look at any connected vertex cover of size at most k, first of all, it contains all vertices here. And second of all, if you add these vertices that you cleverly picked or greedily picked, what you end up with is 1 plus epsilon approximate solution. Is a 1 plus epsilon factor away from the opt of G. That's it. OK, so what about the size? Remember, when we stopped, every vertex here has only at most D neighbors. And the number of components here is at most 2k. And there is no reason keeping twins. Or rather, if you have k plus 1 vertices, each of which have the exact same neighborhood, there is no point keeping all of them because they all have exactly the same connectivity properties, right? Which means that if you have more than k plus 1 such vertices, you can drop one of them. You keep doing this as long as you have such vertices which can be dropped. When you stop, what you end up with is that you have essentially k to the order D neighborhood classes in I, and each neighborhood class has size only k plus 1. And when this happens, the size of G prime is bounded by k to the big O of 1 over epsilon, because D was nothing but order 1 over epsilon. OK? So if you're seeing this for the first time, of course, this will seem really intricate. But the only new thing that you're doing is a very greedy selection of vertices. It just happens that this is sufficient. So the size of the kernel here was k to the big O of 1 over epsilon. But this brings up a question. Should epsilon be in the exponent of k? Why can't it be here and the exponent of k be independent of epsilon? And this is actually an open problem. So if you would like to get your hands dirty with lossy kernels, I suggest to start here. And so just some terminology. Approximate kernels of the kind that we just saw are what are called polynomial size approximate kernelization schemes, the analog of polynomial time approximation schemes in this world. OK, so what we've just seen is a PSAX for connected vertex cover. So in the next 2 to 3 minutes, let me try and reinforce the main idea behind this algorithm by giving you a generalization of this. So let's look at the H hitting set problem. So here H is just a set of fixed subgraphs. It's a finite set of fixed subgraphs. And in this problem, what you want to do is delete vertices so that the remaining graph has no subgraph which is isomorphic to a graph in H. Okay? Why is this a generalization of vertex cover? Because if you just set H to be the single edge, what you're asking is delete vertices such that there are no edges left. This is exactly vertex cover. And so what we've seen is we've seen an approximate kernel for connected H hitting set in this very special case. But this brings up the question, what about in more general case? What if it is not an edge? What if it is something more general? And it turns out that you can generalize pretty much the same argument to this more general problem. And the idea is once again exactly the same. So for now, we are going to forget about the connectivity constraints, go back to the problem without connectivity constraints, look at what people have done. So again, as in the case of vertex cover, it is known that in polynomial time, you can come up with subset of these vertices, such that if you forget about connectivity, you have a kernel here. But if you bring about connectivity constraints, then the vertices here start playing an important role, which is just providing connectivity. So this is the only thing that I want you to take from here. And this is all very well known. And this is just an observation that the vertices here cannot just be removed if you care about connectivity. But again, this brings up the same question. OK, are all vertices important? What if only some of them? If so, how do we detect? How do we identify them? And so on. But again, what came to our help earlier was that we focused only on approximate solutions. So that's exactly what you are going to do now. And what we want here is some way of connecting these vertices or these terminals. So I'm using the word terminals at this moment because I'm trying to jog your memory and somehow relate it to the Steiner tree problem, which we talked about. And here's a quick reminder for people who zoned off then. And if you remember, I mentioned that in 1995, Watchers and Du gave a 1 plus epsilon approximate polynomial kernel for Steiner tree. Don't read this. Just listen to me when I say this, that all you need to do now is take that 1 plus epsilon approximate kernel for Steiner tree and replace your greedy routine that you used in connected vertex cover with this 1 plus epsilon approximate polynomial kernel. And what you end up with is actually a generalization of the PSACs that you saw to a PSACs for this problem. So the only difference is you had this point where you were greedily picking vertices of high degree. You throw out that part and you plug in a known approximate kernelization for Steiner tree. Lo and behold, you're done. OK, so the questions that we've talked about so far have two properties. One is that they are all very hard to approximate. The second is that they are all hard to kernelize. That is, they did not have polynomial kernelizations. But why should one restrict the study to these problems? What are some other problems you could think about if you're working in this framework? And there is actually no reason why you should restrict your study to problems without polynomial kernels or problems without good approximations. You are absolutely valid in studying these problems in the framework of approximate kernels. So here's a quick example of such a problem. So here is the classic dominating set problem, which, if you remember, is nothing but find the vertex set S such that every other vertex is adjacent to a vertex in this set. And degenerate graphs are just a sparse class of graphs. And it is known that there is a d-square approximation for this problem. Well, at least it was. And there is a kernel of size k to the order d square. And it is known that you cannot do better than this. So remember, we had these baselines which sort of told us where our target should be. You should always try to do better than the best approximation factor and try to beat the best kernel size. So these are the two previously best known results. So there's a d square approximate kernel of constant size. There's a 1 approximate kernel of size k to the order d square. Yes?
Is it really 1 approximate kernel?
If you stare at it carefully, yes. So by definition, it isn't. You have to do a little bit of work to get a 1 approximate kernel. OK, so a natural question now is, look at these two endpoints. So is there a nice curve that captures this trade-off between accuracy and the size of the reduced instance? This is a very valid question, even though this is a problem with polynomial kernels. And it is known that for every row, there is a d over rho approximate kernel of size k to the order rho d. So forget about the actual numbers here. The point is that there is a sparse, very coarse interpolation between these two extremes that I mentioned. And there are some new results which make this interpolation obsolete. So this question is still valid. So do not think this question as one that has been answered. I want to pose this question as an open question that you are absolutely free to start working on. And more generally, this is nothing but a special case of the d-hitting set problem. Well, it's not really a special case, but it is closely related to the d-hitting set problem, where you have a d approximate kernel of constant size, because you have a polynomial time d approximation. And there is a one approximate kernel of size k to the order d. This is nothing but the k to the order d kernel. And the question is there a nice curve that interpolates between these two extremes? If not, is there some nice lower bound techniques you can bring into the picture here to tell people what this curve should look like if such a curve exists? So this is one kind of problem where approximate kernels seem very useful. So here's another type. So let's look at the tree with t deletion problem. In this problem, you're given a graph G, and the objective is to delete at most k vertices so that the graph you're left with has tree width at most t. So I promise you that you've seen this problem in some form. What if t equals 0? What is a graph of tree with 0? It's an independent set. So if I ask you to delete k vertices so that the graph has tree with 0, this is nothing but vertex cover. So we really like vertex cover. And if t equals 1, then this is nothing but the feedback vertex set problem, and so on. Now, why am I bringing up this problem? It is known that this problem has a kernel of size k to the sum f of t, where t is the tree width of the final graph you're aiming for. And when you have a kernel of this size, the next question is, does the exponent of k have to depend on t? Can it be removed from the exponent, and can the dependence be in front of k with the exponent being independent of t? It turns out that this is very unlikely that such a kernel exists. Okay, so the next obvious question is, what about approximate kernels? Can we have approximate kernels of this size? Because this lower bound result gives you a baseline for the size of kernel to aim for. So now the question is, can I do better than this? And when it comes to the approximation factor, you have to do as well as you can. And it turns out that there is a very interesting answer to this question, which is yes. To be very honest, even no would be interesting as long as it's accompanied by a proof. And so this is a very interesting result which says that you do have an approximate kernel where the exponent of k does not depend on t. So there are a lot of really interesting refined questions that you can ask for problems which do have polynomial kernels. Okay, so all this time I've been giving you a lot of polynomial kernels. I've been telling you that people have come up with interesting approximate kernels. So does this mean that every problem has an approximate polynomial kernel? Do we always win? Is this such a happy world? Turns out no. There are problems for which getting approximate polynomial kernels are also difficult. And this is a problem you might have seen, the longest path problem. This is a notoriously difficult problem to pre-process. And turns out that the longest path problem also happens to be difficult to pre-process, even if you try to look at the best of both worlds. And this is something that we are not going to talk about today, but a quick question: what could be some way of showing such lower bounds? Is there any way of inferring lower bounds without doing any extra work at this moment? Because it's really late and I can see people are super tired. So without doing any extra work, can you start inferring some sort of interesting lower bounds? So if you remember, we had this nice correspondence. So we said that a problem has a polytime approximation if and only if it has a constant size alpha approximate kernel. So if you pick up a problem which you know, under some assumption, does not have a polynomial time alpha approximation, then this statement means that you cannot have an alpha approximate kernel of constant size. It's not very satisfactory, but here is one way of just piggybacking on others' work and inferring approximate kernel lower bounds. What is another way? So here is another thing that we talked about. We said that a problem has an FPT time alpha approximation if and only if it has some alpha approximate kernel. So again, if someone has proof that a problem does not have an FPT time alpha approximation, then this statement immediately means that it cannot have an alpha approximate kernel of any size. And this is something you will see in Daniel's talk on lower bounds in FPT approximation. And when he talks about it, you should quickly turn this sort of an inference into this sort of an inference. So whenever Daniel says this problem does not have an FPT approximation FPT time 2 approximation, then that immediately means that this problem cannot have a 2 approximate kernel of any size. This is just something to keep in mind. So let me wrap up by telling you what I hope you all take back from this talk. So the first point, of course, is very intuitive, but what we've shown here is that mathematically this is very useful and you can actually model it. That allowing a small loss in accuracy not only allows you to speed up computation, it also speeds up pre-processing. And not only speeds up, it allows you to do significantly better pre-processing. The second thing I hope you remember is that there is no reason for you to restrict yourself to problems without polynomial kernels. So even problems with polynomial kernels have very valid, very interesting, sometimes annoyingly difficult lossy kernel questions. And the third thing, in case you're all too happy, let me bring you back down. This does not actually work for all problems. There are problems for which you cannot have alpha approximate kernels, and this you will see in part 2 of this talk. And finally, since you are here, I assume you are interested in, or you already like, or you would like to get to know more about FPT, kernelization, approximation. So I think it's a safe bet that if you like any of these things, you will also like their baby. So if you're an expert in this area and you want tough problems, you have tough problems. Here you are. You should not be going here. And if you are a novice, then head over here. There are many, many such problems. And if you look at the archive version of this paper, there are many explicitly stated open problems to get you started if you need. But otherwise, you have an easy way to make your own open problem. Pick your favorite problem without polynomial kernel. Try to get an approximate kernel. Pick your favorite problem with polynomial kernel. Frame a careful approximate kernel question. Start. OK, so at this point, I should thank you all for your patience and take any questions.